All right. In this hour, we start from introducing the HTTP response message. The response message is quite similar to the request message. However, there's some slight difference. Again, it has 4 different parts. Okay, and the first part is the status line. After the server receives the request message, the server will respond a message with the status line. The status line also is a single line, okay? And at the end of this line, there should be still \r and which stands for an enter. Okay, so all the messages in the response line are all ends with /r and /n right here. Okay, so right here it is the termination characters. The status line can be divided into 3 different fields. Okay, the first one is the protocol, and the second one is status code, and third one is status phrase. That means 200 OK indicates that the response message is OK, and all the following messages that returned to the client is right here at the fourth part of this response message. Okay, and of course there are certain different status code and status phrase. We will look the protocol spec later. And the second part is header lines, and of course there are some other information that the server would like to exchange with the client. So the format is very similar. Okay, we still have the name right here, and here's the white space, and here's the value, right? And it ends up with /r and /n. Okay, but be aware of that all the headers written here, date, server, last modified, e-tag, accept ranges, content length, content type, all those headers must be defined in the HTTP protocol specification. You cannot just simply add whatever you want in the header lines. The corresponding server and corresponding client will not allow to receive any headers that is not specified, not defined in the protocol specification. Okay, so and again, the date right here, Tuesday, September 08. You should use exact format to represent the date. There's a very clearly definition how to represent the date in HTTP protocol. Okay, so after that is the server. Okay, you have to specify what server you are. For example, right here it is an Apache server 2.4.6 in CentOS, which is a Linux operating system, and with there are several different modules right here. Okay, and next one is the last modified. That indicates the file that the client would like to retrieve. The last modified date of this file is, for example, 2016 March 1st, something like that. Okay, and of course there are tons of headers, and however we don't have time to cover all those headers. So part of headers has their definition. You can check it out in the specification. For example, e-tag. Actually, I don't know what it is, but you can check it out in the header field specification, in the HTTP specification. Okay, accept ranges bytes and the content length 2651. That means there will be 2,651 bytes is attached at the fourth part of the response message. Okay, in total there are 2,651 bytes. Okay, and the content type means the data attached right here is a HTML file. The char set is UTF-8. And don't forget that the third part is still the another \r\n. It is another enter. This enter will it is a delimiter that you can understand what is the end of the headlines. Okay, so that is the HTTP response messages, and you may wonder why those HTTP request message and response messages are in are text-based, why they are not binary-based. That's because in the early days, HTTP is a very old protocol, okay, and at that time, parsing a text-based file is relatively easier, and even more. At that time, we don't know if there's any new headers or new messages should be designed or defined in the spec. So text-based protocol is much more easier to extend itself. For example, as we can see that there are 7 different headers in the second part, right? So if you need even more headers, you can simply just insert and enter, and there's a new line, right? You can design or you can define a new headers by you simply just add a new line right here. But if you use a fixed field or a binary-based protocol, it is not that easy for you to add additional field or headers in the fixed field protocol. So text-based is more flexible, and for example, the server right here, the value of server right here, as you can see that there are a lot of strings, okay, a lot of strings in this value. So you can add arbitrary variable length values in that server header, right? So as long as you have enough space to, as long as you have enough space, you can simply just add whatever you want at the value of the server, as long as the end of the line is /r and /n. Okay, so that is and then here is the response status code shown here, but we'd like to see the things in the protocol spec. Okay, I can simply just Google HTTP protocol spec or HTTP RFC, and you can see that HTTP is the RFC number is 2616, and it was invented by the people at the right hand side, right? And usually we say that T. Berners-Lee is the one who invents web. Okay, so he's one of the scholar that define and write such kind of HTTP specification. Okay, and you can see that it is a very long document. Okay, it has defined everything about the HTTP client and HTTP server should align with. So for example, right here, you can see that in chapter number 3, okay, 3.1, it defines the HTTP version. How do you write HTTP version? Usually it should be a 4 capital word, HTTP and /1.1. So you have to specify those format, those definition in this document. Okay, so 3.2 is the URI or 3.2.2 URL. it defines what is a validate URL. It should be start with HTTP / a domain name and some path. You should follow the rules. Okay. So number 3.3, it is a date time format. As I mentioned before, you have to have a specific way to represent the full date or the seconds. Okay, and so on and so forth. Okay, and we can see that in chapter 4. Okay, the HTTP message, right? It specifies there are two different messages, right? In chapter 5, that is the request message. Chapter 6 is the response message. And for all those messages, there are some commonly shared message headers is defined in chapter 4.2, and chapter 4.3 is the body. Okay, and again, in chapter 5, for a request message, you should have a request line. Includes the method you want to use, include the URI, how do you define the URI. And for chapter number 6 is the response message. As we mentioned before, we have status line, we have status code, and the recent phrases. Right. So let's take a look at the request method. So we think, okay, that's it. In chapter 9, it defines how many different methods are used by the HTTP. For example, 9.2 options, 9.3 get, head, post, put, delete, trace, connect. Those are defined method you can use by browser. Okay, and as we mentioned before, we usually use get or post. Okay, we hardly use some other, we seldom use head, put, or delete, those methods. Okay, and after that, chapter number 10, we can see that there are 5 different types of status code. Right, as we mentioned, as in the view graph, it says okay 200 okay, but actually there are several different status code right here. For example, 100 means continue. 101 means switch protocol. That means okay, everything is fine, and just simply keep transferring your messages. Okay. 200 serious. Okay, 200 okay. That means everything's okay, and my your object has been included in the response message in the part 4 section, right? So it's 200 okay, and of course there are some other reply messages. For example, 300 series. Okay, for example, 301, that means the object you like to retrieve has been removed permanently, so I don't know where to find it. Maybe you have to request some other resources, something like that. Okay, and for example, 400 series. Okay, as we mentioned before, you have to define every errors and every exceptions you might encounter, right? So the 400 series means the client error. That means there's something wrong with your request. For example, 300, that's a bad request. The messages you sent to me, I cannot parse it correctly. Maybe there's something wrong with your request. So it's 400 bad request. 404, not found. I believe you have seen this message before. If the URL you specify is, I as a server, okay, the server cannot find the object specified in your request message, then I will reply 404 not found. Okay, for example, for your theory, for some website, okay, it has the authentication process. So if you enter wrong password, for example, maybe the server will return 403, says okay, you cannot access this part of the website. Okay, and that's something like that. And for 500 series, that is the error, but the error is at the server. For example, 500 server internal server error. For example, if you have a website and there is a database, okay, behind the website, so maybe the database is crashed or has some problems, so the server cannot retrieve information from the database server, so that it cannot create the corresponding web page back to the client. So maybe at this time the server will return 500 internal server error back to the client, so the client knows the server is not operated correctly, something like that. So as you can see that you can see that there are tons of definition in the protocol specifications. So make sure you know how to find the definition, right? For example, right here, do you see that 14.19? There's a definition of the e-tag. Okay, so for some homework, okay, there are tons of things right here. Okay, so for some work, there should be one problem that want you to find some specific value used in the HTTP protocol. I think it should be this one, the Q value right here. Okay, the Q value right here. Okay, so you can take a look at the HTTP specification document and trying to find this section, accept language, and try to figure out what is the definition of Q value. So at least one of your homework. Okay, so I think we can pass this one. So that's it. That is the HTTP. Although the specification is quite long, the document is quite long, but we only introduce the most important part, the request message and the response messages. Okay, here is the next topic. We'd like to talk about the state. As we mentioned before, the HTTP protocol is a stateless protocol. That means the server should not, okay, remember anything about your past request, right? But however, in the current internet, okay, a lot of web-based application that wish to remember something. So here we have a new mechanism called cookies. So you read the text by yourself. Okay, we take a look at this one. Okay, this one. Okay, at the left hand side, it is a client, so it is a browser. Right hand side is the ML server. Okay, so at the first place, the client, of course, send a HTTP request message from the client to the server to request certain object or resources. Okay, and server figure out that the client is it is the first time that the client connect to the ML server, so it secretly create an ID 1678. Okay, and it needs certain storage. For example, there's a backend database, and create an entry for this specific client and create a specific token 1678 for this specific user and store those information in backend database. Okay, and then when the server reply the HTTP response message back to the client, okay, there's a specific header will be included in the response message. Okay, the header's name is set cookie and the value is 1678. So after the client receives such kind of cookie, and again the client will find some storage space to store this specific token 1678 for this specific server, for example ml.com. So at both sides, the client knows that token and the server knows which user used this token. Okay, so after that, every time when client send a request to that specific ML server, the request message would carry this specific token by using a new HTTP header cookie. So at the moment when the server receives such kind of information, it will check out with the backend server to see, okay, that is an old client. Okay, it has a token which I gave to the client, and there's nothing wrong with this token. Okay, so after that, when every time the server responds to this specific client or to a specific using this specific token, the server can customize the web pages that be returned returned to the client. Okay, so in this case, no matter this 1 week later or 1 month later, as long as the cookie is not expired, the server can always respond a customized web page depending on the token that the client use. So right here, we can see that the cookies can be used for example, as authorization. After you have done you have to successfully pass the authentication, the server can give you a secret token in the cookie. So every time you use this token, that means you have already passed the authentication process. Or shipping carts. When you add one new item in the shipping cart, okay, and the server will remember it by using cookie mechanism. So for the next time when you again log into the Amazon website, the server will remember what item has been added to the shipping cart, and so on so forth, so on so forth. So you can know that. So I believe you know that currently when you log in your Google account, you don't have to log in to Google account again, because your browser and your web server, which is Google server, both of them know you have already been logged in with a secret token. Okay, so cookie, so somehow cookie HTTP somehow now it is somehow a stateful protocol, but it was a stateless protocol. Okay, so that is. However, there's some disadvantage by using those cookies. For example, at the backend database or at in your browser, if there's some hackers and they steal the information from your browser, or they hack the backend database, they can retrieve your secret token, right? So they can pretend to be as your browser to communicate with the Amazon server. So the Amazon server will be cheated, right? As long as because you have the secret token. So for example, I think there is an example right here that in 2018, the Facebook. There's some security incident, okay, at the back end of the Facebook. So the Facebook announced that every old tokens is expired. So every user should log into the Facebook website again to retrieve the new tokens. Okay, so they might have some such drawback. Okay, privacy drawbacks. Okay, I think that is one of the I think additional mechanism on the top of HTTP protocol. It was not in HTTP protocol. I think it was 1994. Cookie was invented by a company called NASCAP. Okay, after that, a lot of people, a lot of companies believe that cookie is a very important thing, so we can add the cookie and set cookie, these two specific new headers into the HTTP specification. Okay, but in the first place, we don't have these two headers. Okay, so next part is another additional mechanism which is built on the top of HTTP. Okay, think about one thing. For example, we have a LAN right here. Okay, for example, that is campus network. Okay, so for example, there are thousands of students in for example, in a dorm. Okay, one day, one of the students send a request to, for example, yahoo.com. Okay, to retrieve the homepage of yahoo.com. Okay, so it will access the LAN and go to the internet by using the access link and route in the internet and get the pages from the Yahoo web server, right? But how many students are there in the campus or in the dorm? There may be thousands, right? So if everyone send a request, HTTP request to the access link and to the internet via all those routers and at the end to the Yahoo web server to retrieve the first pages, it seems like that it's a little bit, you know, time wasting, right? And because all of them retrieve the same pages, exactly the same page. So it wastes bandwidth, it wastes the time, something like that. So there's another mechanism called web cache. Okay, web cache means you can set up a machine in your local area network, in your LAN, in the campus, or in the dorm. Okay, so every time, for example, the first student, right, who want to retrieve the yahoo.com, the front page. Okay, so it sent the HTTP request message not to the yahoo.com. It sent the request to the local web cache server. Okay, it has another name called proxy. Okay, proxy and web cache, they are interchangeable. Okay, the client used the green connection and ask, do you have the first page of yahoo.com? And at that moment, the web cache, the proxy, may not have the pages, right? So it will further set up another new HTTP connection to the original Yahoo server to retrieve the first page, right? And after that, it will store the pages in its local storage. For example, it's a database, or it's a file, or it's just a stored on a disk. Okay, and after that, again, the web cache will send the corresponding first page back to the client. Okay, so we have several different colors right here. Make sure you understand the different colors has different meanings. Okay, so if there is another student request, which is the orange one, okay, request the Yahoo first page, and the web cache, the proxy right now, it has a copy of the first page, right? So it will return the page locally. The web cache will no need to retrieve the pages again from the original Yahoo server. Okay, so after that, for the third client, fourth, 5, 6, for example, thousands of clients, when they want to access the pages, the first page at yahoo.com, the web cache, the proxy, can serve them locally rather than get the pages, okay, from the internet. So we believe that is a more efficient way to distribute the pages, of course, the same pages. If some client requests a page that never been stored in the web cache, then the web cache, the proxy, will need to go to the internet and try to figure out where the server is and retrieve the server for that client. Okay, so I think that is quite obvious, very nice design. Okay, so right here, and again, the web cache acts as both client and server. Take a look at these pages. Okay, for the orange one and the green purple one, the web cache, the proxy, act as a server, right? Because it can serve those two web clients. But when the web cache, the proxy, trying to retrieve the information, the web page from the original Google Yahoo.com, it acts as a client, web client, right, to retrieve the information, right? So the web cache, the proxy, acts as both client and server. Server for original requesting client, and as a client to the origin server. Okay, so the when it retrieves the information from the original server, the server tells the cache, the proxy, about objects allowable caching in response header. So there are two other headers in the response message. It specifies how many seconds, okay, the object, okay, the page or the reference object is still valid, okay, or the server tells the cache that this object should not be cached, something like that. Okay, so of course the advantage of applying to deploy in web proxy in your LAN is quite obvious. For example, to reduce the response time for client requests, because for the second, third, fourth, for all the file-in clients who want to retrieve the pages in the web cache, it only needs to retrieve the information, retrieve the object from the local cache server. And as we know, the local bandwidth is much bigger, much larger than the internet access link, right? So the cache is closer to the client. Okay, and second, reduce traffic on an institution's access link, because part of the request will stay in the local area network LAN. No need to access the access link, right? So reduce the traffic. And since we reduce the internet traffic, the internet is dense with caches. So it enables poor content providers to more efficiently to deliver content. So there will be less requests in the internet, right? So the server will have less stress to serve all the clients all over the internet. Okay, so here we have some mathematics questions. Okay, for example, right here, and as you can see, we have a LAN right here, so that is your LAN, right? And in the LAN we have a larger bandwidth, which is 1 gigabit per second. However, the outgoing access link is only 1.54 megabit per second. This is quite small, right? So first access link rate is 1.54 megabit per second. And the second one is that the RTT, which is the round trip time, right? From the institution's router is right here, from this purple machine to the original server, and round trip go back. It takes 2 seconds. It takes 2 seconds. Okay, so of course these 2 seconds include several different delays: transmission delay, propagation delay, queuing delay. No matter how, no matter which part it is, the total delay, total round trip time is 2 seconds. Okay, third and the third one and the fourth one, okay, on the average, okay, the web object size is 100K bits. That means when you retrieve a file, image, no matter what, the average object size, okay, and the response message is 100K bit. And again, on the average, all the users in the institution, their request rate is 15 objects per second. So we time this value, right? So in total, the number is, on the average, the data rate, requesting rate is 1.5 Mbps. Okay, one object, its size is 100K bits, and on the average, for 1 second, they need to request 15 objects. So on the average, in total, it should be 1.5 megabit per second. And as you can see that the SS link utilization, in total, the bandwidth is 1.54, right? But however, currently your browser needs to consume 1.50 megabit per second. So the utilization is 97%. That means 97% of time the link is busy. They are busy trying to retrieve those objects. It could be a problem because when the utilization is high, you know, it is a router, so the queue size may become even not the queue size. I mean the items queued in the queue side in the queue will be larger. It will be longer and longer. So eventually, because such kind of high link utilization, eventually the queue will explode. Okay, the queue will be full. Okay, so in this case, you can see that. How about the LAN utilization? Because we have 1.5 megabit per second request. However, we have 1 gigabit per second LAN bandwidth. So the utilization is very small, like here. So how about end-to-end delay? And to retrieve all those objects, okay, it takes 2 seconds to traverse from our router to the original server, right? And again, because we have a queue at our router and our utilization is 97%, so eventually the queue is full. So you may need to take more than 1 minute to wait in the queue. Of course, it is just a approximate value. Maybe it takes a few seconds or 10 seconds, 20 seconds. We don't know, but we simply just write. The textbook just simply write it down. Says it takes a minute to wait in the queue, and then in the LAN, okay, it only takes several milliseconds to transmit your request from your browser to the gateway. So basically, three different delay. The first one is the purple one, and for the light green one, the main one is Q right here, right? Q right here, and that's the one is the LAN delay. Okay, that's how you connect it, how you transfer your messages from your client to the edge router. So how did you deal with such kind of problem? Because you have only very limited. You have only limited outgoing access link. Okay, here's the option one. It's quite straightforward. That means you spend more money to enlarge your outgoing access link bandwidth from 1.45 megabit per second to 154 megabit per second. So every number right here changes to 154. So your link utilization decrease. Since you have a very small link utilization, then your queue must be empty or nearly empty. So you don't have to wait 10 seconds, 20 seconds, or a minute to wait to be transferred in the router. So maybe it only takes few milliseconds. However, you have to think about one thing. To have a faster access link, it is quite expensive, right? It is 100 times cost if you upgrade your small link to 100 times access link. So it is a okay solution, but it takes a lot of, it's quite expensive. Okay, so let's take a look at option number 2. Okay, we use these pages. Okay, so now we set up a local web cache in your van. Okay, and we like to introduce this number, hit rate. As we mentioned before, every time when you ask your local web cache to retrieve some web pages, and the local web page will make a copy and save it to its local storage, right? But for long term, it is not necessary that the pages has been retrieved by some other clients and has already been saved in the storage, right? So the hit rate right here means there are 40% right here. There are 40% of requests can be served by the local web cache. Okay, and the 60% of the request, they still need to go to the original servers and to retrieve the objects from the original server and pass it to this very small access link. So let's assume the hit rate is 40%. Okay, so for 60% of the requests, they should go to the internet, right? So on the average, right here, the original request rate is 1.5 megabit per second, right? But currently, only 60% of the requests need to go through the access link. So on the average, only 0.9 million bits per second traffic will go through this access link, right? So right here, we can see that the utilization becomes 58%, right? 58%. Originally, it is 97%, right? Now it is 58%. For 58% link, we believe that the queue may not increase so dramatically. So maybe it has a shorter queue, but the waiting time will be dramatically shortened. Okay, so we can think about one thing. If we want to calculate the average end-to-end delay, so we have two parts right here. Okay, for the first part, 60% of the pages still need to go to the original servers through the 1.54 megabit per second access link. So 60%, and the delay right here, it should be 2 seconds plus, right? Certain delay. But right here, we don't have minutes. We don't have minutes queuing delay, because currently the link utilization is only 58%, so we don't have to wait so long. So for example, in textbook, it says, okay, we only need to wait 2 seconds. 2 seconds is for the round trip time. We only need to wait few milliseconds. Okay, so that is 2.01. And 40% of the pages, they don't have to go to the internet. The web cache can serve the clients. Okay, so 0.5 parts of the pages, they only need to several milliseconds, and they can be served by the local web cache. So on the average, it is 1.2 sec. So if you establish a local web cache in your LAN, it is more cheaper, for example, to rather than buying 100 times bandwidth. Okay, so it is more cheaper to set up such kind of local web cache, but your network environment is still good enough to serve all those thousands or hundreds of clients. Okay, the average end-to-end delay is lower, right? But you don't have to pay a lot of money to upgrade your bandwidth. Okay, so that is the web cache. Okay, that is the content of this hour. We will stop right here because all the things will be all the other things will be discussed in the next hour. So we stop right here. Okay,